So example 1, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. So here I have a diagram of an open box. Now they said the base is square, but they didn't say anything about the entire box being square. It's not a cube, not necessarily. It could be, could not be. So in the picture, they assigned the length and width as x, and then the height is h. What dimensions will produce a box with maximum volume? Okay, so first of all, start off trying to locate the information that they gave you. They told you that the surface area of the box is 108. So you're going to use the surface area formula. It's just easier to make one up yourself. Okay, surface area are all the surfaces and their areas added up, right? So the bottom is a square. So that area is x times x. So x times x is x squared. So that takes care of the surface of the bottom, right? The bottom surface. And then the other sides, there's only 4 other sides because this is an open box. It doesn't have a top. The other 4 sides are x by h. Right? So this side right here is x by h. So all 4 of them are actually x by h. And there's 4 of them. So 4x by h. And we know what the surface area equals. It equals 108. Next stop. What is it that we're doing in this problem? What dimensions will produce a box with maximum volume? So we're going to need volume and we're going to maximize it. Now, let me move this over a little. Okay, so this is surface area. Right, so volume. So volume is length times width times height. Once again, the length and the width here are both x because the bottom, the base, is actually a square. So length times width, so x times x, so x squared times height. So there's my volume. I don't know what it equals because that's what I'm trying to maximize. Okay, so my primary equation is the volume. My secondary equation is the surface area. Right? I'm going to use the secondary equation. Okay, so surface area is my secondary equation. I'm going to use that to solve for one of the variables because the whole point of there being 2 equations is that we don't want to work with 2 variables. We want to work with just one. So I've decided that I'm going to solve for h. Solving for h means I'm going to get the h by itself. So all my answer will be x's, right? My answer will have the x's in it. So to start off, subtract x squared. So I have 108 minus x squared. And then divide by 4x. So I have that. And then simplify if possible. I think usually you should be able to simplify. 108 divided by 4x. 108 is definitely divisible by 4. So it's 27. But then the x can't go anywhere, so it stays. And then minus, and then x squared divided by 4x. The 4 is going to stay, but the x squared is divisible by x. So I'm just going to have x over 4 or 1/4 x. Okay, so that is my h. So now I'm going to take that and plug it in here. Okay, these problems are the same as the problems from before, just that now it's volume and surface area. That's all. All right, so volume is now x squared times 27 over x minus 1/4 x. Of course, you need to simplify that because it's yucky. So multiply x squared, or FOIL it out, however you want to say it. So x squared times 27. So I'll write it all out. I get 27 x squared over x, and then minus, and then 1/4 x cubed. Now the 27 x squared over x, I hope it's obvious that one of the x's do actually cancel out. So I have 27 over x minus 1/4 x cubed. So there's my volume. In order to find the x, right, that will actually give me a minimum or a maximum, depending on what they asked you for, I need to derive. So take the derivative of your equation, and you get 27 minus 3/4 x squared. And then take that derivative and find the solution for x to zeros. So you set it equal to 0 to find your zeros. Okay, add the 3/4 x squared to both sides, and you get 27 equals 3/4 x squared, or just 3/4 x squared equals 27. Get rid of the 3/4 by doing 4/3. Right, multiplying by the reciprocal. These cancel out, and you have x squared equals. Now let's see, 27 times 4 divided by 3, or 3 goes into 3 once, and 3 goes into 27 9 times, right? So 9 times 4, and that's 36. So x squared equals 36. So x is actually positive or negative 6, but this is volume and surface area. We wouldn't have a negative number, so x would be 6. All right, you do have to make sure, and I realize that it's kind of annoying because it always works out that it is the maximum or the minimum, whatever they asked you to find. But what if they didn't tell you if it was a max or a min? You would have to know how to figure it out. Very quickly, do a sign chart and pick two values, two test values, one to the left and one to the right of 6. And then we're going to plug it in here to the derivative, because the sign chart is the sign chart of the first derivative. So we're going to plug it into the first derivative. I'm going to pick 0, right? Becomes positive. And then let's see, a friendly number. Some friendly number. So I think a friendly number would be like 10. Right? So I plug in 0, I get 27 minus 0. So it's positive. When I plug in 10, I get 27 minus 3/4 times 100. So that's 300 divided by 4. 4 goes into 375 times. So 27 minus 75. That's definitely negative. Doesn't really matter what number it is. So I'm going up and then coming down. So this is a max. And most likely that is what they asked me to do, maximize, right? So I'm maximizing the volume. And it usually does work out that way from all the problems I've seen. So this is definitely a max, and because it is a max, I may proceed with answering the question. They wanted the dimensions. So the dimensions of this box would have been x times x, in inches, I believe, times h. Oh, that looks too much like a times h. So x is 6, so 6 inches times 6 inches times, and of course if I want to find h, I'm going to have to plug it in. Let's find, there's h right there in the blue. Okay, this is what I'm going to have to use to find h. I'm going to write it over here. So h equals 27 over x, which is 6, minus 1/4 times x, which is 6. So let's see. 27 divided by 6. So that's 24, it's 4.5. Minus, and then 6, well, 1/4 times 6 is 6 over 4, which I believe is just 1.5, if I'm correct. 6/4 is 3/2. Okay, 4.5 minus 1.5 is a big whopping 3. So there are my dimensions, 6 by 6 by 3. Okay, next. A manufacturer wants to design an open box having a square base and a surface area of 48 square inches. What dimensions will produce a box with a maximum volume? See, if I were you, I would stop this video now and I would actually try to figure out what your two formulas are, or equations. And if you wanted to draw a picture, you were more than free to, but you could just actually use the picture from example 1. Okay, so here are the two equations I'd hope that you'd figure out on your own. They are exactly the same equations as example 1. The only thing that is different is the surface area in this problem is 48. So once again, the surface area is our secondary equation, whereas the volume is our primary. That is the one that we have to maximize. That's the one we're going to derive. Once again, it has two variables. We want to get rid of one of the variables. So we're going to use our secondary equation to get rid of one of the variables. And again, I'm going to choose to solve for h. I want to keep it all with x's. Okay, so 4xh equals 48 minus x squared. So then h is 48 minus x squared divided by 4x. And then I can simplify that. 48 divided by 4x, so it's 12 over x. And then negative x squared divided by 4x. The 4 stays. I'm just going to write it as a 1/4, and then I have an x. So very similar to before, only that the 12 is different because the 48 is different than whatever was before. I forgot what it was already. 108, something like that. Okay, so that's my h. Now I take my h and I plug it into the volume so that I have a new equation. Well, actually, it's an old equation. I'm not going to have any h's in it. So x squared times the stuff that h equals, which is 12 over x minus 1/4 x. All right, so I'm going to distribute, make this equation a little easier to derive. So x squared, so I'll write it all out, over x minus 1/4 x cubed. Okay, so 12x squared, the x's in the first part can cancel out, so I have 12x minus 1/4 x cubed. So there's my equation. That's what I'm going to derive. All right, so derive it. You know what? Let me do it in another color. I'm going to go ahead and derive my volume. So 12 minus 3/4 x squared. Take your derivative. Find your x's by setting it equal to 0. So I could subtract 12 from both sides. I end up with negative 3/4 x squared equals negative 12. Or I can move the negative 3/4 to the other side. I just prefer to be like, okay, it's going to end up positive if I move the 3/4. Get rid of the 3/4 by multiplying by 4/3. These cancel out. And I get x squared equals, let's see, 12 times 4 is 48. 48 divided by 3 is 16. Or, 3 goes into 3 one time. 3 goes into 12 4 times. 4 times 4 is 16, whichever. Let's take the square root of both sides. Technically, x is plus or minus 4. But we're dealing with actual lengths and stuff, so positive 4 is what we're going to use. Make sure that this is, in fact, a maximum. I believe that's what we were asked to do. Maximize the volume. Yep. So I'll plug in 0 again. And what number is friendly? I'll do 10. So plug in 0. I'm plugging it into here, the derivative, right? So 12 minus 0 is a positive number. It's 12. And then plug in 10. I get 12 minus, let's see, 3/4 times 10 squared. 10 squared is 100. So it's 3 times 100. So 300 divided by 4, again, is 75. So 12 minus 75, definitely a really big negative number. This is a max. So we're good to go because that's what we're supposed to do. And my dimensions are Remember, so it was x times h. So x is 4, so 4 inches times 4 inches times h. I actually need to find h. So here is how we're going to find h. So 12 divided by 4 minus 1/4 times 4. So 12 divided by 4 is 3, minus 1/4 of 4 is 1, so that's 2. So h is 2. So 2 inches. And there are my dimensions for that. All right, next example. Okay, so we found our dimensions. Next. Example 3. An open rectangular box is formed by cutting congruent squares from the corners of a piece of cardboard and folding up the sides. If the original piece of cardboard was 24 inches by 45 inches, what are the dimensions of the box with maximum volume? Okay, so example 3 is an example where you do not need a primary and secondary equation. Sometimes it is the case that you actually don't have enough information to make two different formulas or equations out of. So in this equation, all I know is that the original piece of cardboard has dimensions of 24 by 45. So, well, I think this is a little big. Let me make this smaller. Okay. So initially, from here to here, it's 24 inches. And then from here to here, it's 45 inches. Now, they're cutting out this square from each corner. Squares have equal sides, so let's go ahead and call them x by x because we don't know what they are, but we at least know that they're squares, so the dimensions are the same. So now, what I really have is when these get folded up, the dimensions from here to here will not be 45 any longer. They'll be 45 minus an x from each corner, so 2x. And then for here, my dimensions won't be 24. They'll be 24 minus an x from each corner. So those will be my dimensions from my box. You can call it length and width if you want. The length and the width will be 45 minus 2x and 24 minus 2x. The height, when I fold these corners up, the height will be the x, that little square that I cut out. So the only thing I have here is enough information to write out a formula for for volume. Holy crap. For volume. I'm going to maximize the volume. I don't have any other pieces of information. So let's see how it goes. So volume is length times width times height. So 45 minus 2x, because let's call that the length. The width will be the 24 minus 2x. And the height is just a little x. All right, so I've got my length, my width times height. And so again, I repeat, I don't have enough information for another equation. I don't have a secondary equation. Usually what do we do with the secondary equation? All right, so as I was saying, this secondary equation, we always use it to get rid of one of the variables because we only want to deal with one variable, not two. But if you notice in this problem, I only have one variable. They're all x's. There aren't any y's, there aren't h's, there aren't anything else. So because I only have one variable, it is okay to not have a second equation because I won't need it, at least for what we use it for. So in order to maximize the volume, I'm going to still take the volume, I'm going to derive it, set it equal to 0, make sure that that is my maximum, and I can find my dimensions from there. Now, the volume equation is icky, So we're going to have to clean that up. And so you're going to have to foil and all that good stuff. And since I already did that, I'm just going to go ahead and write it. So once I foil this out, and I'll do it in 2 steps. So here was me foiling out the X with the first, or sorry, let me redo that. On my paper, I foiled that out and I got 24x minus 2x squared. And then 45 minus 2x. And then when I foiled that out, I got 4x cubed minus 138x squared plus 1080x. And that is cleaned up. So make sure you can do that. All right, so derive. We must now derive our volume. So I get 12x squared. 2 times 138 is 276. And then 1080. I'm going to set this equal to 0, and I'm going to find x. Now these numbers look scary, but chances are they have some kind of common factor. And hopefully, using your common sense, you would try out 12. So pull out the 12. 276 divided by 12 is 23. And then 1080 divided by 12 is 90. So now I have to factor. I need 2 numbers that multiply up to 90. Right? I call it the AB method, or sorry, ACB method. Can't even talk. So A times C, so A is 1, C is 90. So 90. B is the negative 23. I need 2 numbers that multiply up to 90, but add up to negative 23. So hopefully you're like, okay, 2 times 45, that won't work. 6 times 15, that doesn't quite work. 12 times 15, that doesn't work. So then I end up with 5. And, do I have enough space? 5 times 18. Now if I add 5 and 18, I do get 23. But I have to get negative 23, so they both have to be negative, because when I multiply them, I get positive 90, so we're good. So I got x minus 5 and x minus 18. All right. Zero product property, I get x equals 5 and x equals 18. Now look at these numbers. X is 18. Should not make sense, because I would be cutting out a square. Like this little square right here would be 18 by 18. Leaving behind a lot less, I guess the length and the width of the box would be compromised to be even smaller. So most likely that's not going to hold the most volume. But no big deal, because the way we figure out which is the maximum is by doing a sign chart. Alright, so I picked the numbers 1 and 10 and 20. And then I plug them in. And for 1, I got a plus. I got a positive number. For 10, I got a minus. And for 20, I got a positive number. So let's see what's happening here. Plus minus, that's a maximum. Minus plus, that's a minimum. So max, min. I was supposed to maximize the volume. So x equals 5 will do that. The 18 will not. I was also supposed to find the dimensions. So dimensions of my box. Okay. let me go back up here real quick. Remember, I want to know what the dimensions of the box are going to be, not what the original dimensions of the cardboard. So not 45 and not 24. I'm going to use 45 minus 2x and 24 minus 2x. That'll be my length and my width, and then x will be my height. So length, width, height. Okay? So x is 5. This was inches, right? Yes. Length and width, really doesn't matter which one you pick as what. So 24 minus 2x. So it's 24 minus 2 times 5. So 24 minus 10. So it's 14. Let's put that here. And then the other is 45 minus 10. So let's put that here. So my dimensions would be 35 by 14 by 5. And those are the dimensions that will actually maximize the volume of this box. Okay. Last one. An open rectangular box has a square base and a volume of 500 cubic inches. What dimensions minimize the amount of cardboard needed to make the box? Okay, so look at what you got. It's an open rectangular box, so just like the previous examples. They're telling me that the volume is 500 cubic inches. So the volume is 500. Again, it's a rectangular box with a square base, so I can use the same exact formulas as before. So the volume formulas that we were using was the bottom was x times x. Sorry, not the bottom. The length and the width were x times x, and then the height was just h. And that equals 500. Let's see what else they told us. What dimensions minimize? So we're looking for a min. The amount of cardboard needed to make the box. When we're talking about material needed to make a box, we're not talking about volume, we're talking about surface area. I'm going to call S for surface area. And I get to use the same exact equations as before. The bottom was x times x. There is no top because it says that it's open. Okay, so no top. And then there are 4 sides that are x times h. So there's my surface area. That is my primary equation. I do not know what it equals. This is what I'm trying to minimize. Okay, I'm trying to minimize surface area. So this is my primary equation. My secondary equation I'm going to use to eliminate one of the variables, because in this problem we do have 2 different variables, x and h. I want to go ahead and solve for h. So 500 over x squared. That way I can avoid doing square roots. Okay, so there's my h. So I'm going to go ahead and plug it in over here in my surface area. So x squared plus 4 times x times h, which is 500 x squared over x squared, sorry. All right, let's simplify this a little bit. X squared plus, this x eliminates one of these. And then 4 times 500 is 2,000. And that's going to be over x. So there's my equation. With only one variable in it, I'm going to go ahead and derive. So I get 2x. And then if you derive 200 over x, okay, little side note here. 2,000 over x is really 2,000 times x to the negative 1 power. If I want to derive that, bring the negative 1 to the front and multiply, so negative 2,000. And then subtract an exponent. But then we can rewrite that. The negative 2 means it's actually the denominator. So negative 2,000 over x squared. Okay, just a little side note just in case. So back to over here. So this plus is not supposed to be there. So minus 2,000 over x squared. So there's my derivative. I'm going to set it equal to 0. And I'm going to move the 2x over, or the negative 2,000. Let's move that one. So 2x equals 2,000 over x squared. Best way to do this is to cross multiply. So I get 2x cubed equals 2,000. Divide by 2 both sides. And I get 1,000. And then I have to cube root. And cube root. If you think about it, one number times itself again gets me 1,000. So the cube root would be 10, because 10 times 10 is 100. 100 times 10 is 1,000. So there is my x. I'm supposed to be minimizing, so let me be a good girl and check and make sure that this is in fact the minimum. And I'll pick a number to the left and a number to the right. I'll pick 1 and 100. And the reason I'm picking 100 is because of what the derivative looks like. You could pick 11. Go ahead. No big deal. But you're plugging it in here, right? So if I pick 1, I get 2 minus 2,000. 2 minus 2,000 is definitely a big old negative number. If I plug in the 100 that I like so much, I get 200 minus 2,000 divided by 1,000. Or is that right? Let me make sure I'm saying what I'm saying. So I get 200, 2 times 100 minus 2,000 over, 10,000, my bad. So 2,000 over 10,000 is really just 1/5. So 200 minus 0.2 is still a really big number, right? So it's still positive, no negative. So at 10, we're going down, and then we're coming back up. And this is definitely a minimum. So I am doing what I was supposed to. Now it says what dimensions. So if I have my x, I need to find my h. Let's go back up. I have enough room. So here is how I'm going to find h. So my dimensions for this box, since it has a square base, that means x times h. Right? So x, I already forgot what x was. Holy crap. 10. So 10 inches by 10 inches by, and then I have to figure out what h is. So let's see what h is. H is equal to 500 divided by 10 squared, which is 500, divided by 100, which is so conveniently 5. So there you go. All right. Optimization is really not that bad. Okay. Please do your homework, whatever.